Hey, what's good, Logan? All right, so this video is for Sophie. Thanks for asking for it. This question is, what is end behavior? Like, how does that work? What were the notes on for today? So this is what's happening. Suppose we have this function here, f of x equals x to the power of 4 plus x to the power of 3 plus x plus 1. All right, so we got that guy right there. And the question is what happens as we plug in bigger numbers or smaller numbers, right? So that's the question. What happens do we plug in numbers that go to infinity, or when we plug that numbers that go into negative infinity, that start getting really, really big or really, really small? Well, this one is fairly straightforward. Like if you plug in one, you're going to get a 1 to the power of 4, a 1 to the power of 3. Essentially, you're going to get a bunch of ones, and we're going to get 5. And then what happens when we plug in 2? When we plug in 2, we're going to get 2 to the power of 4, which is 16, and then we're going to get 2 to the power of 3, which is 8, 2 to the power of 2, which is 4, 2, and then plus 1. So we're going to add up all those, and we're going to get some value. And it doesn't look like our numbers are going to get smaller. It looks like it's going to consistently get larger, right? We can keep doing this. Sorry, I didn't add those up. It's just kind of lazy. We could plug in 10. So let's say we plugged in 10. We would now have 11,111. And that's by plugging in 10. So imagine what happens if we plugged in something like 100, right? So we're plugging in numbers that are getting bigger and bigger. And the y value is just skyrocketing. So it's almost like as the x gets really, really big, right? So as the x gets bigger and bigger and bigger, it feels like the y is kind of doing the same thing. Now, some of you might be looking at this and say, yeah, no duh, that makes a lot of sense because all you're doing is adding stuff together. The question then is what happens if we weren't adding things together, right? So what if we weren't adding them, but what if we were actually subtracting them? So we're going to go x to the fourth, take away the x to the power of 3, take away the x squared, take away the x, and then take away the 1. What if we did that, right? And when you do this, what we end up finding out is that when you start off with 1, you end up getting something on the negative side. We get something around, negative 3. And then when we plug in 10, we're going to get 10,000, take away 1,000, take away 100, take away 10, and take away 1. Now, I can see that all of these are less than 1,000. So I could approximate it as, it's definitely going to be less than 8. It's going to be more, sorry, not less, more than 8,000. So when I plug in 10, it's 8,000. And we can start to see that this number is already starting to get bigger, right? So we plug in 100 now. And when we plug in 100, what we end up getting is, I have no idea. I'm just going to write a bunch of zeros until I get the right number of zeros in there. And then we'll say what that value is. Oh my God, that's 100 million. So 100 to the power of 4 is 100 million. And then we're going to subtract, yeah, not a whole lot. We're going to subtract 1 million from that. So it's going to be 100 million, take away a million. Oh, and then we can assume that everything over here is going to be less than a million. So, worst case scenario, we're going to say that 2 million is what we're looking at here. This thing is now at 98, 98 million. Yeah. So we're looking at huge amounts of value here, right? So 98 million. So even when you have that, on the negatives on the numbers after it, that number in the front is ridiculously large. Now, some of you are like, but those numbers in the back have no value. Like, there's no coefficients. Okay, fine. So now we could try this whole exact thing over again with coefficients. So, we could put like whatever we want here, like a 10 here, and then we could put like another 10 here, and then another 10 here, and we get the same exact effect, right? When we plug in 0, yeah, we get negative 1. And then when we plug in 10, we're definitely going to get a negative value here. So this is going to be some negative value. If I had to give you an answer, I'd say probably that number right there. And you're like, see, now if you put those 10s there, now notice that it's actually getting smaller. But we've only plugged in 10. Now let's plug in 100. And the moment we plug in 100, the number starts to get positive again. If you don't believe me, you can go ahead and plug it into a table, right? Set up your favorite Desmos table and then just type in, get rid of that y and get rid of the 1 that's over there and just keep it as x. And then just go x to the power of 4 minus 10x to the power of 3 minus 10x squared minus 10x minus 1. And then, just plug in numbers, plug in 100, and then plug in 1,000, and then plug in 10,000 just to see what this thing does. And you're going to start to see that as your numbers get really big on the x values, your numbers on the y values get really big. And now, what does this mean? What it's telling us is that regardless of what we're looking at behind the leading term is really deciding what's happening with the really large numbers. And the same thing is true about the small numbers. So when we do our analysis for end behavior or for really big values, the lead term is going to do all of that for us. It's going to do all of the analysis that we need. All right, so I revamped the notes. I've redesigned them to be a little bit different. So this might look familiar. This is in Jamboard, but I'm going to update it with this newer version here. So end behavior is an analysis of a function that describes, right? It's describing what's going to happen when you get really big x's, positive infinity. Also, when you get really small x's or negative infinity. Now, the most important thing to remember here is that the lead term is going to decide the end behavior. It's going to tell us everything we need to know about end behavior. Now, the lead term is going to have two things going on with it. It's going to have the lead coefficient, which can either be positive or negative, and then it's going to have a degree, which either can be odd or even. So one more time, the analysis, the thing that we're looking for is the lead coefficient to either be positive or to be negative. That's one of two things that's going to happen. And then the degree of the polynomial, we either care if it's even or if it's odd. Okay, so those are the two things we care about. Now, what we're going to first look at is the lead coefficient. So we're going to pay heavy attention to that guy right there when we start off the problem. Now, you'll notice that I wrote down some hands over here. So we got some hands going on. And what we want to start off with is the right hand. So we're always going to start off with the right hand, deciding what's going to happen with the right side of the graph. Now, if I go back to the problem we were looking at earlier, this guy here, when it was positive, the right side of the graph was skyrocketing up. If this was negative, the right side of the graph would tank or go down. And this is what we're going to write as our end behavior analysis. We're going to say that if the lead coefficient, right, so if this guy here, if the lead coefficient is positive, then the right side of the graph is going to go up. So the lead coefficient is positive, the right side goes up. But if the lead side is negative, if the lead coefficient is negative, then the right side of your graph is going to go down. Okay, make sense of that, right? If you plug in really big numbers and the lead is positive, yes, you're going to get a positive answer. But if the lead is negative, you're going to get a negative answer. That makes sense. Now, let's talk about the degree of the polynomial. So the degree of the polynomial is going to dictate what happens on the left hand. And it's a really simple process. If it's even, it's going to follow what the right hand does. All right, let me explain. So let's suppose you had something that looks like this. Your lead coefficient was 6x. Let's not make it 6. Let's try something different. Let's go with 61x to the power of 8. So 61x to the power of 8. So your lead coefficient is positive, which is why the right side of the graph is going to point up. But because the degree is even, the left side of the graph is going to match it. So the left side will match what the right side is doing when the degree is even, no matter what. So if the degree is even, we're going to match the right side. But if the degree is odd, then the right side, we're not going to match the right side. Odd, we're going to go in the opposite direction. So when you have a lead coefficient that's positive, the right side will go up, but the left side is dependent upon the degree of the polynomial. And if it's even like this, then we're going to go up. But if it was odd, let's say it was 11, then it would have gone down. And that's how we're going to analyze our end behavior when you have a lead coefficient that is positive. Now, what if the lead coefficient was negative, right? Then our right hand is going to go down. But our degree is going to determine whether or not our left hand follows it. So if the degree is even, we will match our right side. The left hand will match the right side. And if it's odd, then the left hand will be in the opposite direction of our right hand. And this is how we define our end behavior. Now, the next thing we need to do is make sure we understand how to write the words up, down, left, and right in mathematical terminology. So your right-hand side is always going to be written as x goes to positive infinity. One more time. The right-hand side will always be associated with x goes to positive infinity. And the left-hand side will always, I'm missing something over here. I made a mistake in my notes. We got to erase that. Because the left-hand side will always be associated with x going to negative infinity. So let me just fix that right there. the left-hand side, right, x goes to negative infinity. Now, if you're trying to say something is going up, then you're going to say f of x goes to infinity positively. And if you're trying to say down, you're going to say f of x goes to negative infinity. All right, now let's practice it. So in question number 7, I've just drawn the graph for you. You'll notice that on the right side of the graph, it's going up. And on the left side of the graph, it's going down. So what I would say is on the left, sorry, that's not the left, on the left-hand side, right, the left-hand side, and that's common terminology you'll see in other math courses, and the right-hand side. Now, on the right-hand side, we notice that it's going up. But on the left-hand side, we notice that the graph is going down. So now we're going to write our analysis in math terminology. What we'll say is that f of x is going to negative infinity. That's how we say down. And we're going to say it's going down as the x is on the left-hand side, which means x is on the negative infinity side. But then we have our right hand, or we have our right side end behavior, which says that the function, the graph, goes up to positive infinity as the x is on the right-hand side, as x goes to positive infinity. Now, that's how you look at it when you see the graph. But what if we didn't see the graph? What if we had the function like we have in question number 8? You'll notice that the lead coefficient, it is written in the correct order. The lead coefficient is 0.25 x to the power of 3. Now, since it's positive, right? So since the lead coefficient is positive, I know what's going to happen on the right-handed side. So on the right-hand side, I know my graph is going to go up. But because it's a negative degree, because it's an odd degree, my mistake, the left-hand side is not going to go up, it's going to go down in the opposite direction. So remember, right-hand side is when this guy here is positive or negative, and the left-hand side is going to be the degree whether or not we match or go in the opposite direction of our right-hand side. And now we can write it in the correct notation. So we're going to say that the function goes down. So we're going to say f of x goes to negative infinity as x, let me write the word x as x goes, not x, as x goes to negative infinity. So the graph goes down on the left-hand side. Now, on the right-hand side, f of x, right, it's going to be going up over here. F of x goes up to positive infinity as x, oh, forgot the as part, as the x, as we go to the right side, which means x is going to positive infinity. All right, let's try one more question. Number 9, notice the lead coefficient, the lead term, is negative 3x to the fourth. It is written in the correct order, so it is in standard form. And we have our left side, right? So we have our left-hand side, and we have our right-hand side. And we notice that on the right-hand side, since this guy, the lead coefficient, the lead term, is negative, the right-hand side will have to go down. But because the degree of the polynomial is even, we know the left-hand side will have to match it, because even degree will always match what the right-hand side does, whereas odd degree, as in question number 8, does not match it, but goes in the opposite direction. All right, so now we can write it on the left-hand side. F of x is going to go down. So f of x is going to go towards negative infinity as x goes to the right, the left, which is negative infinity. That kind of looks like all the other ones we've seen before, except it was dependent upon the degree and the right-hand side. So now we're going to write down what the right-hand side does. Well, the right-hand side also goes down in this scenario. So f of x goes down to negative infinity as x goes to the right, which is positive infinity. And this is how we look at end behavior and analyze it. Notice we don't use any of the rest of the polynomial, we just use the lead term, because the lead term tells, he's kind of like a bully, he tells the whole function what he wants to do when he gets really, really big numbers and really, really small numbers. All right, last problem. I want you guys to graph these things. Yeah, this video is going to take a while. The way that I want you to graph them is a horrible technique. It is a technique for beginners. So what you're going to do is you're going to make a table of values. I would pick numbers between -3 and +3. You're going to plot the points and connect them with a smooth curve. Also, you're going to want to make sure that your end behavior is preserved. That means it's the same end behavior. So if I was looking at number 10, we're not going to do 11 today. If I was looking at number 10, my analysis would say that it is in the correct form, and I know that the lead coefficient is positive. So I know that my right-hand side, actually maybe I should write it over here, I know that the right-hand side is going to be going up, and I know that the left-hand side, because the degree is odd, right, because it's an odd exponent, is going to be going down, the opposite of what's happening on the right-hand side. So right-hand side up, left-hand side down. All right, now we're going to set up our table. Now, I like adding this information into our table, but it does confuse some students, and I think some teachers be like, don't do that. I'm okay with it. I think it's not a bad idea. So I think we should be plugging in numbers like -3, -2, -1, 0, 1, 2, 3. But I also think we should talk about what happens when x is getting really tiny. X is getting really small. And that's where the left-hand side comes into play. I know that the y is going to decrease. That's what we're saying right here. So on the left side, my y's are going to get really small. So when I plug in -3, there's a good chance I start getting more negatives. Or maybe I need to plug in bigger numbers to get those more negatives to occur. All right, and then I also know that when x starts to get really big, so positive infinity side, I know that the y will also get really big towards the positive infinity side as well. So it'll also go up, and that's because my right-hand side end behavior was determined using the lead coefficient. And then now we're just going to plug in the numbers. I'm going to plug in 0, 0 here, 0 here, 0 here. That's going to give us 2. Next, I'm going to plug in 1. 1 here, 1 here, -4 there, 2 there. That's going to give us, I think that's 0. So we're going to get a 0 right there. Let me just double check one more time. 1 plus 1 plus 2 is 4 minus 4. Yep. Next, I'm going to plug in -1, right? So -1 plus 1 cancels. 4 and 2 is 6. So I'm going to get a 6 over there. Next, I'm going to plug in 2. So this is going to be 8, and then 4, and then -8, and then 2. The 8's cancel, and we get 6. All right, and then we have 3, so we plug in 3, that's going to be 27, and then 9, and then -12, and then 2. Let's see, -10, -1, 26, it looks like. And then I'll plug in -2, that's going to be -8, +4, +8, and then +2. The 8's will cancel out, give us 6 over here. That's weird, but we'll see the weirdness in a second. And then -3, we'll plug it in, that's -27, +9, +12, +2. That's going to come out to 27, negative minus 23, I believe. And that's going to be -4 right there. All right. And I think if we start plugging more numbers in for the -3, go to -4, -5, -6, you're going to start to see that they start creeping up more negatively. And then the 26, they're going to start creeping up more positively after you plug in 3. All right, so now that we've got our table of values, we can go ahead and set up our x and our y axis. So I'm going to set up my y axis, and I'm going to set up my x axis. All right, now a couple of things. I'm not trying to graph this thing super accurately, but I could with the exception of that guy right there. That guy's kind of wonky, super big, so I'm probably going to avoid that guy. But I'll graph the other points, -3, -4. Looks like that guy right there. And then we got -2, 6, something right there. And then -1, 6. That's kind of goofy, but whatevs. And then 0, 2. So 0, 2, kind of right there. 1, 0, right about there. 2, 6. So 2, 6 is chilling. Wow, lots of 6s up in this one. So 2, 6 is chilling up there. And then 3, 26 is just hella high up there, right? So it's way up there. But that's kind of good because our right hand end behavior is supposed to skyrocket. And it's kind of doing that. And our left hand is supposed to, tank down in that direction. All right, so now you're kind of playing connect the dots, but you're not doing connect the dots like you were in second grade. You're going to do connect the dots like you're in high school. You're going to like smooth out the curves. You're not going to get all zigzaggy like a goofball. All right, so we're going to set up our point and we're just going to start connecting. So I'm like, la, 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 connect it to smooth out the curve, smoothing out the curve. And then we kind of get something. Yeah, that's all I really need you to do. Make sure that your end behavior is preserved so that low left-hand side yeah, it's going down. And the right-hand side, yeah, it's going up. Now, if your end behavior is not preserved, you're going to have to plug in bigger points or smaller points. So you might have to pick points bigger than 3 and smaller than -3. But the way I designed the assignment, it's probably going to be okay. And this is how you graph using like really low level skill here. So it's an introductory to graphing polynomials. It's to help us understand that end behavior decides what's happening on the right side and the left side. However, what happens in the middle of the graph, that's kind of being determined by the guys after the lead coefficient. He's kind of those guys with the lead coefficient, of course, the lead term as well, but those guys are trying to kind of move the graph up and down. It's making it very random. But then when you start getting bigger numbers, it becomes less random, or smaller numbers become less random. We have a tendency now. We're going bigger to infinity, or we're going smaller to -infinity. All right, this is a long one. I'm sorry about that. Hopefully this is helpful. If not, hit me up tomorrow. I wish you guys the best of luck, and I'll see you later.